Okay, so today's lesson is the first part of lesson 2.2. So we're split this into three sections. So density curve, um, we're talking about one in particular, a very popular density curve in a minute, but let's just start with the idea. It's always above the axis. It kind of models the data you have, the shape of the data you have. Um, It always has area of exactly one. That actually is kind of important. We'll do a lot of calculations with that. What percentage is past a certain number? So the area under the curve, this, if you take calculus, that might sound a little bit like calculus right there. But um, so we're going to use that to make, estimates and observations about data. So here's a group of data that has kind of an interesting look to it. If we made a density curve for that data, we would probably say it's somewhat uniform, and so you could draw a straight line across, and that would be the density curve. The height is 1/3 because the width there, or length, whatever you want to call it there, is between 2 and 5, which is 3. 3 times 1/3 is 1. It has to add up to 1, so we knew the height had to be exactly 1. Much more common. So this is the famous one. This is the normal curve. A lot of data has this kind of a look to it. We can do a lot of calculations if it does have this look to it. So this is about 7th grade students on the vocabulary part of the Iowa test. And standardized test scores actually very much fall under a normal curve. They have this kind of shape to them. So SAT scores, ACT scores, all those kinds of standardized tests, and lots of times even tests in the classroom have this kind of a look to the data. A lot of folks around the mean, somewhat symmetrical, and kind of spread out. So the mean is the balance point. The median, of course, is the middle. There's equal areas on each side. It cuts it exactly 50%. If it's symmetrical, the mean and median should be about the same. That's a concept we've learned a couple times. If it's skewed, we know that the mean is going to get pulled with that skew. It's going to get pulled to the right in this case because this is right skewed. And that would not be normal curve there, right? Normal curve on the left, that would be true. So the mean and mean are the same, so that's what I just said. Okay. So, and it's idealized. I think that's kind of true. So a normal curve is an idealized curve. So the actual data is a little bit more messy. This is more of a perfect kind of model for typical data when it seems approximately normal. So when we talk about the mean of a density curve, the density curve is kind of like the population. It's kind of like the idealized thing. So we use mu for that. And we use, again, Greek letters. We're talking about the population. So this is kind of like the population, kind of like the idealized or perfect world kind of thing here. Standard deviation is sigma. Okay, so these are both considered approximately normal curves. And one is taller than the other. That's okay. But they have the shape is symmetric, somewhat bell-shaped. It has a mean and standard deviation there. So what's true about all normal distributions? The shape is symmetric, single-peaked, and bell-shaped. The center is the mean. It's also at the midpoint. So the mean and median are about the same for a perfect density curve. That's the same. And variability measures, again, we're talking about deviation to the mean. So that standard deviation, that sigma, is the width of one deviation there. Okay, why are they important? Well, here's some reasons. We use them a lot. So a lot of stuff, a lot of data ends up looking approximately normal. We typically will use the word approximately normal because no data really is perfectly normal. They just tend to be approximate. So take a lot of measurements of something, stuff produced in a factory, whatever that is, whether it be tennis balls or something else, it's probably going to be approximately normal. They're good approximations of chances. So tossing coins, rolling dice, all those kinds of things oftentimes end up looking normal. Certainly a lot of our spring work, starting in the spring, will be about inference, and we use normal approximations all the time. So this is a foundational skill. This is kind of like the empirical rule. This is kind of like a rule of thumb we use that's pretty accurate. It's not perfectly accurate, but it's pretty accurate, and it's a good approximation. We can do a lot of calculations just without even our calculator if we know this for the empirical rule. So the number of standard deviations out. So if you go one standard deviation out, now notice, and this is really important, you get this. Some students, when they first learn this, don't get this. So 0 is the mean in this case. If you go 1, it is measured in standard deviations. That's our x-axis measurement. If you go 1 standard deviation to the right and 1 standard deviation to the left, so that's called 1 standard deviation, but we're really going in both directions. So 1 standard deviation is 68% of the data because it's falling within 1 standard deviation when you go in both directions from the mean. 2 standard deviations, so that includes the 1 standard deviation plus some extra there. 2 standard deviations away from the mean includes most of the data, 95%. It's probably why we usually, if something's more than 2 standard deviations away from the mean, we usually call it unusual, outlier kind of thing, because that's unusual. But man, 3 standard deviations, if you're more than 3 standard deviations away from the mean, that is super unusual, right? So that is, because 99.7% of the data for a perfect normal curve falls within that. So only 0.3% fall into that little sliver off to each side. So 0.15% technically to each side there. Only use the empirical rule with normal distributions. If it's skewed, do not use the empirical rule. Only works on approximately normal. So this is what we want to see. So you see a problem like this. So so we can measure it 2 different ways. You can actually use the standard deviation and mu, or you can convert it to a standardized score. This is helpful. Let's say you wanted to see, maybe you got a 30 on the ACT and you got a 700 on the math section of the SAT. You want to compare those scores. Which one's better? If we knew the mean and standard deviation of those tests, which we can actually figure out, you could compare the scores and figure out which one's the better score by looking at the z-score. So it's a standardized score so that it kind of makes all the scales the same. So the scale is always the same for standardized z-score. So 0's in the middle, that's the mean, and you always go by 1 standard deviation in each direction. So you go 1 standard deviation, that's the ruler. You're measuring in standard deviations, where 0 is the center or the mean. And so here, it's the same data, but we've converted the scores by using this conversion. So we'll look at what that looks like in a minute. So how do you do this? How do you find the area? So draw a normal distribution. Make sure that you scale it, with standard deviation kind of scales. Perform calculations, show your work. We'll look at what this looks like, and then be sure to answer the question that was asked. That's true. Okay. So first thing, so if you want to draw this, so we know that the mean is 6.84 for these Iowa test scores, and the standard deviation is 1.55. So you start by drawing a normal curve, and in the middle, if you see that 6.84, you put in the middle, then you get your calculator out, and you would just start going, okay, so 6.84 plus 1.55 plus 1.55, and do that a few times. So that's where these numbers come from. Do you see the 8.39 there to the, and then we have the 9.94, the 11.49. If you take the mean, 6.84, and subtract 1.55, sometimes I'll type it like that. And now, do you notice when I type 1.55, it says answer minus. So now when I press enter, it's going to do that same calculation 3 times. So it'll give me the bottom 3 numbers on the standard deviations there. So using actual numbers. To convert, so So, and this is just a standardized score there. So to figure out what the z-score of 6 is. So if we want to figure out what 6 is, so we do the fraction. It's that same z-score we've done from the other section. So the value 6 minus the mean, which is 6.84, over the standard deviation, which was 1.55. And we get negative 0.54. So that's where we knew how to draw this. So we went, if we consider 0 to negative 1 there, negative 0.54 is about there. And so we're going to draw that line up right there and shade appropriately because they want that score or lower than that score, I believe, for this one. So that's how you convert from, to find out what that 6 value is, in z-score terms, you have to use that equation. Okay, so so how do we do this with a calculator? So let's get our calculator out and show you how to do this. So to do this in the calculator, what you do is you go to Menu, Statistics, Distributions, number 5, and there it is, Norm CDF. So the nice thing, it has a wizard that kind of walks you through here. It defaults to negative infinity, which is what we want here. To the left, the lower bound is negative infinity. The upper bound, it looks like, is using this one is negative 0.54, negative 0.54. And we're going to leave the default of 0 and 1 because this is a z-score. So when you use a z-score, just kind of leave the default at 0 and 1 and say OK. And the actual area under the curve there is 29.45%, right? 0.2945. We could also do that another way. So we don't have to convert to z-score. We could have used the original. So let's try that. So go to Menu, Statistics, Distributions, Norm CDF is the second choice. And this time we're going to use negative infinity because that is, and if you're wondering what we're doing, we're taking this one on the left here. So you see this one on the left? We're using that picture here. So for the upper bound, we're going to say, well, the upper bound is just 6. But our mean, we do know our mean. It's 6.84. And our standard deviation for that one, I believe, was 1.55. And now we're going to say OK. And it should give us the same exact answer. So you can figure out the area under the curve using Norm CDF, if it's approximately normal, using the normal curve, either in z-scores or using the actual numbers. And it's pretty easy either way using your calculator. So that's actually very nice. You can use a table that the ACT or the APSTAT gives you, but it's so much easier using a calculator. Be sure to answer the question, right? So what proportion of these 7th graders have that? And so 29.4% approximately of the, and then you're parroting back the question, the context of the question of Gary, Indiana 7th grade scores fall below that for the ITBS vocabulary test. Okay, so let's try one, see if you can do it. So here's chapter 1 test for Mrs. Gala's first hour class. The scores were approximately normal with a mean of 81 and a standard deviation of 6. So I want you to be able to sketch a normal curve. Go 3 standard deviations out in each direction, in both directions. You need to do that. This one should be a little easier. There's no decimals here. So you'd start with that 81 in the middle. You go 6 to the right, 6 more, mark those scores, put a label on it. Chapter 1 test scores go 6, 6, 6 in the other direction as well, subtracting 6 each time from the mean of 81. That's a really nice normal curve. Notice that the curve almost ends there at 3 standard deviation, 3 standard deviation. Remember, 99.7% of the data, approximately, is under the normal curve there. So it should kind of end right about there. There's 3 deviations in each direction, so we say that's 3 standard deviations out. So this is a separate question. So again, we're assuming that the scores are approximately normal. That was given to us. We don't have to prove it. But what percent of students scored greater than 69? So this says use the empirical rule. So 69 is right there. That's 2 standard deviations below the mean, right? So using the empirical rule, we know that the data, 68% was within 1 standard deviation, 95% within 2. So 95% goes from 69 all the way to 93 there. So there's only 5% that's not in there. So that'd be 2.5% to each side. So if you think about it that way, 95% is that shaded area plus each side has 2.5%. So if you add the shaded area plus the right side, that 2.5%, you get 97.5%. There's really only that 2.5% on the left there. So most of the scores, students were 69 or better on this test. Second question was, now use your TI Inspire to find the percent of students who scored. So if we want to use our Inspire, so let's try that. So if you want to use your Inspire, so we go to menu, 652. We don't want our negative infinity here. We want 69 is our lowest number there. To a max of, don't say 99. It really needs to go to infinity technically. So we're going to go infinity. If you have the ACT calculator, the non-CAS, you have to say a big number like 99999. Mean, I think, was given to us here. It was 81. Standard deviation looks like it was 6. And if you say OK, that's going to give you... So notice, this is more accurate than our empirical rule estimation. We thought 97.5. It's actually 97.7%. So empirical rule is more of an estimation. Calculator can always give you that pretty close to exact there. Okay, so then we also could have converted, right? So let's try to convert this. So it's good practice for us. So we wanted 69. So 69 minus the mean of 81. All over the standard deviation of 6. Put a decimal, so it gives me a decimal. Oh, it's exactly -2. Wow. So it's exactly -2. So now we can use, we know that the z-score is -2 here. So let's use that way. So menu 6, 5, 2. Okay, so we want from -2 z-score all the way to infinity. The pi key and choose infinity. And you can leave the default because we're doing z-scores here, and it should give you that same exact answer. So two different ways of calculating, but that's how it looks like. There it is. Okay, a student scored 69 would be at what percentile? So remember, 97.5% is to the right of that. So I guess 2.5% is to the left. So they're in the 2.5 percentile? 2.5th percentile? That's a funny thing to say. Is because it's 100 minus that. So they're not in a very high percentile there if they got a 69 on the test. That is your lesson for today.